In this work, we develop a data-driven stochastic model for realistic rendering of splashes due to water drops. Here we see water drops falling on different materials. The resulting splashes vary significantly in the number of ejected droplets and their distributions over time and space. The dynamics of a splash depend on the roughness, rigidity, and wetness of the material. We have designed an apparatus to measure the distribution of droplets produced by a splash. Water drops are produced using a drop generator. The drops fall on a sample, and the resulting splashes are imaged by a camera from close to the generator. Just beneath the sample, a thin horizontal sheet of light is created using 3 digital projectors. The captured video reveals the location and time at which each splash droplet passes through the illuminated sheet. This information is used to estimate the parabolic 3D trajectories of all the splash droplets. Here we show the captured videos for samples of rusted iron and silk. Here are the corresponding 3D visualizations of the measured droplet trajectories. The splash distribution depends strongly on the surface inclination. Here we see measured splashes for a rubber sample as its inclination varies from 0 to 40 degrees. Notice how the inclination affects the number of ejected droplets and their trajectories. We have measured the material and inclination dependency of splashes for 22 real-world materials. These materials can be broadly classified as rough, such as wood and brick, smooth, such as glass and plastic, non-rigid, such as fabric and paper, and miscellaneous, such as moss and mud. For each material, 10 splashes were measured for each of 6 inclinations between 0 and 50 degrees. Using these measurements, we have developed a compact stochastic model for rendering raindrop splashes. For each material, our splash measurements give us the number of droplets, their velocity magnitudes, and their elevation and azimuthal angles. For each of the parameters, a distribution is computed with respect to the surface inclination alpha and azimuthal angle phi. Well-known probability models from fluid dynamics are fit to the distributions to obtain their means and standard deviations. These means and standard deviations vary smoothly with alpha and phi. We use low-order polynomial surfaces to represent these variations.
The final model requires 7 coefficients for generating splashes for head-on impact for a given material. For rendering splashes for arbitrary inclinations, our model requires 54 coefficients.
Here we show splashes simulated using our model for concrete and metal. On the left, we show the actual splash measurements for comparison. Here we see simulated splashes for 2 more materials, umbrella cloth and cardboard. As we can see, the simulated and measured splashes match well. Our splash models can be linearly combined to generate physically plausible splashes for novel materials. Here we show splashes obtained using different combinations of our metal and rust models. Our splash model gives intuitive controls for modifying splashes. For example, by simply changing the mean elevation angle, we can generate splashes that appear flat or bouncy. The user can also exaggerate the effects of surface inclination. Here we show splashes rendered using our model. The falling drop and the splash droplets are rendered as transparent spheres illuminated by an environment map. Note that the rendered splashes are realistic in terms of their distributions as well as their appearance.
Here is another scene with splashes rendered on 3 different materials. Brick produces a large number of droplets. Splashes from metal appear bouncy, while splashes from plastic are flat.
We now show examples of introducing raindrop splashes in images and videos of real scenes. Here is a captured video of a wet car. The user provides a rough depth map, scene illumination, and a rough segmentation of the different materials in the scene. Here is the scene rendered with just rain. With the splashes missing, the rain appears disconnected with the scene elements. We now add splashes generated using our model. Notice how the splashes vary with material and inclination. For example, notice the bouncy splashes from the metal hood, the small splashes from the wool cap, and large splashes from the newspaper. Also notice the effects of surface inclination on the glass windshield and the newspaper.
Here is a backyard scene rendered with rain and splashes. Notice how the plastic chair produces very few droplets with low velocities. In contrast, the rough brick and concrete surfaces produce much larger number of droplets with higher velocities. Here we show the close-ups of different materials in the scene. In this work, we have measured the splashing behavior of 22 real-world materials. Using these measurements, we have developed a compact stochastic model for rendering water drop splashes. The model was then used to efficiently render raindrop splashes in images and videos.